I'm not sure how to do that. Is this a little bit better?
No, it's fine anyways as it is. So.
How do you do? Is there a full screen function somewhere?
I'm sure there's a Mac OS user here.
Let me see. Yeah. Let me see if there's a way.
Oh, so the same thing probably is what happens to Anton. Just stop sharing, and instead of sharing a window, share the full screen so that you can actually go full screen. But it's not so important, Andrews. Anyway.
Okay, yeah, I don't totally see. So maybe I'll just do it the way that I was.
That's fine.
Okay, shall I start?
Yeah, I'm not sure on Mac, but maybe if you if you stop sharing and then do full screen, and then try to share a window, you'll see two options. One is the window, and the other is the full screen of the PDF. If you know what I mean.
Yeah. Let me see. Okay, so I guess the first thing is try to make this thing full screen. Okay, now.
Yeah, I guess you're right. Just go back to sharing and then full screen it.
I still don't see that. Let me try this and see if that's better.
It's the same, Andrew, but it's fine. We can see it.
Okay. All right. Shall I get started?
Yeah. So we have Andrew Linshaw, who's going to tell us about vertex algebras and arc spaces.
Okay. Thanks very much to the organizers for inviting me here. So this is based on joint work with Bayo and Song. Most of it is in our recent series of papers. There's a few set results that that are not in the papers that I'll talk about. And my title is perhaps misleading. I initially thought I would say more general things about the connection between arc spaces and vertex algebras, but I decided to focus on just one type of result. So that my outline is I'll state the results without explaining exactly what the notation means. Then I'll go back and talk about background and notation. Then I'll say a little bit about arc spaces. And the main ingredient here is the invariant theory of arc spaces. Okay, so the main result has to do with classical freeness. So some of these things have been discussed in previous talks, but I'll try to use similar notation. So for every vertex algebra, there are two geometric objects that Arakawa has defined. One of them is the associated scheme, which is just the spec of Jou's commutative ring. And of course, we also have the associated variety, which is the reduced scheme of x tilde v. And then we also have the singular support, which is the spec of the associated graded algebra with respect to Lee's canonical filtration. And for any V, there's always a closed embedding of the singular support in the arc space of the associated scheme. And the question of when this is an isomorphism was, I think, initially raised by Arakawa and Moreau. And this has turned out to be an important property in work of Ekeren and Heluani on chiral homology. And so they give this a name. They say that V is classically free if these two are equal. And initially, this is defined for just vertex algebras, but how Lee has extended this naturally to vertex superalgebras. So the main result is a class of examples of simple affine VOAs where this holds. So for all non-negative integers m and all positive integers n and r, with a certain condition on these quantities, minus m over 2 plus r plus n plus 1 should be positive. This affine superalgebra, simple affine superalgebra at level n of OSP M2R is classically free. And so there are certain special cases that are maybe more important. So if M is 0, then this is just a VOA of symplectic type, affine vertex algebra of symplectic type. So these are rational affine VOAs, and these are all classically free. And also if M equals 1, then these are rational affine superalgebras of OSP 1, 2, and these are also classically free. So this generalizes a case of SL2, which is due to Ekeren and Heluani. And in general, it's expected that simple affine VOAs at positive integer levels should be classically free, but I only know how to prove this for type C, and I'll say a few words later about why I don't have the same methods don't seem to work for the other types. Okay, so this is the main result. So let me now go back and say a little bit of background. So most of the vertex algebras that one meets are strongly generated by some finite set. And it's useful to have strong generators rather than just generators for a VOA. What does it mean to be strongly generated? So it means that as a vector space, V is spanned by all the normally ordered monomials in the generators and their derivatives. So another way to say this also is that the OPEs of these generators close perhaps non-linearly, but all the terms in the OPE of any two of these generators can be written as linear combinations of such monomials. So we can think of this as essentially this says that V is generated by these its generators as a differential algebra under the normally ordered product. And there's also a notion of free generation. So we say that these generators freely generate V if these monomials that I've written down form a basis. So in other words, we have a PBW basis for the VOA. And then as a vector space, V is isomorphic to a differential polynomial algebra. So not every VOA is freely generated. Even not every VOA is even the quotient of something freely generated, but many interesting examples are. And so here's a partial list of known freely generated VOAs. So we first of all have the free field algebra. So we have Heisenberg algebra, beta gamma system, free fermion algebra, and symplectic fermion algebra. We also have the universal affine vertex algebra. So this is, I think, this notation that's been used in some previous talks associated to a simple Lie algebra G, or Lie superalgebra. We also have the universal W-algebra associated to G and nilpotent element. And G also could be a Lie superalgebra. Okay, so the simplest nonlinear example, so the generators for the affine VOAs close linearly under OPE. And for free field algebras, the only non-trivial term that appears in the OPEs among the generators is the vacuum. But W-algebras are more interesting in the sense that the OPEs are nonlinear. And the first such example is the so-called W3 algebra. This is the principal W-algebra of SL3. So this has two generators, a Virasoro field and a weight 3 primary field, and they have some OPE, which is a little bit nonlinear. And you can also take tensor products of any of these examples to get something freely generated. In fact, these are basically all the examples that I know of that are finitely generated, but there are much more exotic VOAs that have infinitely many strong generators that are freely generated that I won't talk about. Okay, so for any VOA, we can talk about Jou's commutative algebra. So this has come up in a few talks. I'll just very briefly say what it is. So we take the vector space quotient of V by the span of all things that are of this form, some derivative of something, possibly normal ordered product with something else. So this is the same as A minus 2B. This is sometimes called the like C2 of V, and the vector space quotient has a structure of a commutative associative algebra. It's inherited by the normal ordered products. And the map from V to its quotient sends A to A bar. Okay, so it's easy to see if you write down the associator and commutators with respect to the normal ordered product that the failure of this product to be associated and commutative lives in this C of V. So the quotient is a commutative algebra. This is called Jou's commutative algebra. And Arakawa defines the associated scheme of V to be spec of RV and the associated variety to be the reduced scheme. And the reason why strong generators for VOAs are useful, one reason at least, is that strong generators for V give rise to generators for Jou's commutative algebra. In particular, V is strongly finitely generated if and only if these objects are of finite type. Okay, so what does this look like in a few basic examples? So for the Heisenberg algebra, Jou's commutative algebra is just polynomial ring on one generator. Associated variety is just the affine line. For a universal affine vertex algebra, G's commutative algebra is polynomials on G star, and associated variety is just G, which you can also identify with G star. And for the W3 algebra with these two generators, the G commutative algebra is just the polynomial ring. They have no relations, and the associated variety is C2. And in general, if V is freely generated by some set of fields, then the G commutative algebra is a polynomial ring, and the associated variety is just an affine space. If V is strongly but not freely generated by some collection, then the associated variety, the G commutative algebra, it's generated by corresponding elements, but then we have some ideal of relations. Typically, it's difficult to describe this ideal I. There are examples where it's known. For example, if I take the W3 algebra at a special point, say take level minus 3/2, this is the one where the central charge is -2. So this is no longer simple. It's generically simple, but it's not simple at this point. And the simple quotient has a relation, and it turns out that the associated variety is just polynomial ring mod this ideal, W squared minus L cubed. So it's just a cuspidal curve. Okay, so I'm going to talk about something completely different and then return to vertex algebra. So I want to say a few words about arc spaces, and this also has come up. So this is a construction in algebraic geometry that's supposed to be the analog of the construction of jet bundles in differential geometry. So let's say that X is some scheme of finite type. I'm going to work over C, but it could be any algebraically closed field. It doesn't even have to be characteristic 0. So there's another scheme that I'll call X infinity, called the arc space of X. And maybe the best way to characterize it is by its functor of points. So what this says is that if I take a commutative ring A, the A-valued points of the arc space X infinity are in bijection with the A of T valued points of X. And this is the ring of Taylor series in T. Okay. And so from this definition, it's apparent that this construction is functorial. So if you have a map of schemes, you get an induced map of arc spaces. If X is an affine scheme, suppose that X is spec R for R, some finitely presented commutative ring, then it turns out that X infinity is also an affine scheme, and we can actually write down a presentation of it. So let me try to explain how this goes. So the C valued points of X infinity are supposed to be the same thing as C of T valued points of X. So what is a morphism from spec C of T to X? X is a spec of this ring. That's just a ring homomorphism from this rings, polynomials in X1 through Xn mod some ideal to C of T. Okay, so how do I characterize such ring homomorphisms? Well, they're determined by their values on the generators. So the generators of R are X1 through Xn. And so phi of Xi, that's supposed to be some power series. I can write it in this way. It's Xi0 plus Xi1t plus Xi2t squared, et cetera. So this is some series in T. And I've given a name to the coefficients. I'm calling them Xi0, Xi1, Xi2, et cetera. Okay, so the fact that phi is a ring homomorphism means that there's some constraints on what phi of Xi can be. They have to satisfy these generators of the ideal. So because this is a ring homomorphism, each of these FLs, when I plug in the corresponding power series, phi of X1 through phi of Xn, I have to get 0. Okay, so this is some complicated expression, but for each power of T, I can collect I can collect the T to the I power, and there's only a finite set of terms in front of it. This is a condition on these coefficients, which I'll tell you in a moment what that condition is, if there's a nice description of it. So these Xij's for J greater than or equal to 0, I'm going to think of these as coordinate functions on. And so this big polynomial ring on Xij for all J greater than or equal to 0, this is a differential graded ring. It has a derivation that I can define first on the generators. And there are different ways there's different normalizations of this. Sometimes in a bunch of papers, this is, I have a factor of j plus 1, but I'm going to throw it out in characteristic 0. It doesn't matter. So this d simply raises the j index to j plus 1. And so then I can extend it by the Leibniz rule to monomials, and then I can extend it linearly to the whole polynomial ring. So I have a differential on this polynomial ring. And so here's an example to see how this acts. So here's a x1, 3. This is like the third derivative of x1 times x2, 4 cubed. This is the cube of the fourth derivative of x2, plus something to the 7, 2 times something to the 7, is x3, fifth derivative. So how does this act? Well, it's going to act by the Leibniz rules. So it acts on x1, 3 by taking it to x1, 4. It just raises this index. So the way that so it's x1, 4 times this factor. And then by the Leibniz rule, I have x1, 3 times the derivative of this factor. So that's supposed to be 3 times x2, 4 squared times the derivative of x2, 4, which is just x2, 5. And in this piece, there's 7 times 2 is 14, x3, 5 to the 6. The derivative of x3, 5 is x3, 6. This is just an example to illustrate how this works. Okay, so now that this polynomial ring has a differential, I can talk about the derivative of any polynomial, in particular these FLs that were define the ideal of relations in R. I can take their derivatives, and FLR means the rth derivative of FL. That's some polynomial here. Okay, so it's not difficult to check that this requirement that FL, when I plug in the power series corresponding to x1 through xn, this is 0. That translates to the following condition, that if I take these FLs and I take their rth derivative as a polynomial in the various, the ring in the generator is xij, this is 0. Okay, so you collect terms and you can show this. So this tells us how to write x infinity as an affine scheme. So it's going to be the spec of a ring that I'll call R infinity. It's just the polynomial ring on x1 through xn and their jth derivatives, mod f1 through fk and all their derivatives as well. Okay, so at least for an affine scheme, x infinity is affine. This is our description of it. And we can also identify xi, the generators of R, with xi0. And so we naturally have an embedding of R into R infinity. And by construction, R generates R infinity as a differential algebra because R infinity is generated by all the derivatives of x1 through xn. The ideal of relations among xij is a differential ideal, and it's generated by the relations in R as a differential ideal. So in fact, this R infinity can be characterized by a universal property. It's the biggest differential ring generated by R in this sense. If S is any differential commutative ring that contains R and is generated by R differentially, then S is a quotient of R infinity. Okay. So let me go back to the vertex algebras now. So I mentioned before, and this has come up a few times, every vertex algebra has Lee's canonical filtration. So this is a decreasing filtration where the p-th filtered piece is spanned by products of some elements with a certain number of derivatives, where the sum of the n1, n2 through nr is greater than or equal to p, so at least p derivatives. So of course, f0 is just v, and the derivative sends fp to fp plus 1. So one can take an associated graded object. It's the sum of fp minus fp plus 1. And there's a projection of fp onto the pth graded piece of the graded algebra. Okay, so this is a differential graded commutative ring. And you can naturally define, if you have something of filtration degree p and something of degree q, how do you multiply these? Well, you take the normal ordered product and then you project onto the p plus q piece. And there's also, what does the differential do? It takes, I take A, I take its derivative, and then I project to the p plus 1th piece. Okay, so the 0th graded piece, f0 mod f1, is just Jou's commutative algebra, because this f1 is another name for the Jou ideal that I called C of V. And it turns out, it's not very difficult to show this, that RV generates the graded algebra as a differential algebra. Okay, so for freely generated algebras, it's pretty easy to see that the associated graded algebra is just a differential polynomial ring on the generators. So for Heisenberg algebra with one generator, the graded algebra is just polynomials and this generator and its derivatives. And similarly for affine VOAs and for W-algebras, we have a similar description. Yeah, in general, V is freely generated, and the graded algebra is just a differential polynomial ring. If the vertex algebra is strongly generated but not freely generated by some collection, then it's a lot harder to describe the graded algebra. So it's certainly true that it's the quotient of, because the graded algebra is generated by alpha 1 through alpha n as a differential ring, it's generated by alpha and its derivatives. And there's some ideal, but it's very difficult to describe this I in general. Even some examples where we should be able to do it, we actually can't. So one example that I mentioned before, the W3 algebra at this level, where the central charge is -2. This I, well, it contains the relation. W2 minus L3 was a relation in Jou's commutative algebra. So it has this relation and then all the derivatives of this relation. That's actually not everything. But a complete description of this I is not known even in such a basic example.
Andy, I have one question, Dražen.
Yeah.
So, is it known what is maximal ideal in this singlet model? So we have one vector at conformal weight 6.
Yeah.
So it gives you this ideal.
It should. I don't think that's a theorem, but I think that that must be true, that generates the ideal.
And then you have problem in proving that this is complete ideal?
I think it's not, I don't know this, a proof that is the whole ideal.
Yeah.
Yeah, I don't know. My guess is that it is, but I don't know a proof of it. Do you? Does anyone else?
No, I just noticed this. So I know that there's one vector on formal weight 6, but it is not known. I don't know if it is known that this is maximal ideal generated by this vector.
Not to me.
Yeah.
I thought about this at some point. I wasn't able to prove it. So yeah, I don't know. Maybe somebody else knows, but yeah, to me it's not.
Okay, thank you.
Yeah. So one of the things that's interesting in this example is that if you take the arc space of this cuspidal curve, the arc space is actually not reduced. So there's some nilpotent elements in the ring of functions in the arc space, and we also don't know what the nil radical is for this arc space, but all the nilpotent elements that are obvious to write down, they are 0 in this graded algebra. So I even don't know that the graded algebra is reduced in this case. I do know, in fact, that that if you pass to the reduced algebras, then the arc space, this graded algebra is the same as the reduced ring of the functions on the arc space. But the issues are scheme theoretically, I don't understand either side. Okay, but we can say in general, though, is that because RV generates the graded algebra as a differential algebra, then because of the universal property of RV infinity, we always have a surjection from RV infinity to the graded algebra. And this was mentioned before. Some questions that are natural once you see that you have this surjection. So these questions were raised by Arakawa and Moreau several years ago. So one question is, when is this phi in isomorphism at the level of schemes? And this is what Ekeren and Heluani call classical freeness. And then a slightly weaker but also important question is, when is this induced map, the induced map on reduced rings in isomorphism? So this could be called classical freeness at the level of varieties. And there are many examples where 2 is true, but 1 is not true. And in the case where 2 is true, then it's a natural question to understand the kernel of this map. And the kernel is easily seen to be a differential ideal. And so one of the questions, a basic question is it finitely generated as a differential ideal? Can you write down explicit generators? Okay, so if V is freely generated, it's easy to see that phi is always an isomorphism. If V is simple and quasi-Least, then it has been shown by Arakawa and Moreau that phi is not necessarily an isomorphism, but at the level of reduced rings, it's an isomorphism. And then we have some examples of that. These are due to Van Ekeren and Heluani. There's some examples that are, and these are quite difficult to prove, where phi actually is an isomorphism. And these are all examples of C2 cofinite VOAs. So at the level of reduced rings, there's nothing to prove. But this is these scheme theoretic statements are quite interesting. So they prove that LK SL2 is classically free for all positive integers K. And they also give a complete classification for which Virasoro minimal models are classically free. So Vir2P is always classically free. And the Vir-PQ, where P is bigger than 3, is never classically free. And the first non-trivial case of Vir3-4, with a great deal of work, they're able to show that this kernel is non-trivial, but as a differential ideal, it's generated by just one element. And this is the first example where a complete description of the kernel of this map when it's non-trivial is given, and it's shown to be differentially finitely generated. Okay, so one of the things that I'll do, in addition to generalizing this result for SL2, is to give a bunch more examples where the kernel of this map can be explicitly described and it's differentially finitely generated. Okay, so these are applications of some results in invariant theory of arc spaces that a priori have nothing to do with VOAs. And so let me say a little bit about the invariant theory of arc spaces, and then I'll return to VOA applications. Okay, so the setup is G will be an algebraic group, V will be a finite dimensional G module. A good bit of this theory makes sense over an arbitrary algebraically closed field, not necessarily characteristic 0, but I'm just going to take the field to be C throughout this discussion to make things easier. Okay, so the arc space G infinity is also an algebraic group. It's some big unipotent extension of G. And there's an action of G infinity on V infinity. V infinity is just the arc space of V, the vector space. And the categorical quotient V mod mod G is just the spec of the ring of invariance. And this is always, G is, say, reductive. This is always a finitely generated ring. Okay, and the quotient morphism, we have a quotient map V to V mod mod G. It induces a map of arc spaces from V infinity to the arc space of V mod mod G. And so we get a morphism from V infinity mod mod G infinity to V mod mod G infinity. And this is just the map that corresponds to the ring homomorphism from the ring of invariance. So I take V mod mod G, and then I take the arc space of that. So V mod mod G is spec of CPG. So this is just I take this ring and I take the arc space, the corresponding arc space. It's generated by CVG as a differential algebra. This maps to the G infinity invariance in C of V infinity. Okay, so we have this always for any G and V, we have this map. And so the question is, when is this injective? When is it surjective? When is it an isomorphism? And so the statement that this map is surjective means that the G infinity invariance in here all come from the image of this map. And the image of this map is generated by this CVG. In particular, it's finitely generated by these classical invariants as the differential ring. So the surjectivity gives us generators for this ring of G infinity invariance. The injectivity says that all the relations come from these relations, the classical relations and their derivatives. So in general, it turns out this map is neither injective nor surjective. So for example, if G is any finite group acting non-trivially on some vector space, this map is never surjective. So in fact, the right-hand side, the ring of invariance, is never differentially finitely generated. You can even see this in the example of Z2 acting on a one-dimensional space. The ring of invariance is not differentially finitely generated, whereas the left-hand side is. So it doesn't have to be surjective, but even if it is surjective, it doesn't have to be injective. So there are examples where the V mod mod G infinity is a non-reduced scheme, but the right-hand side is obviously an integral domain because it's a subalgebra, a polynomial ring. So this can fail to be injective or surjective. So there are some criteria that will guarantee that this is an isomorphism, but they're very restrictive. So one such criterion is that V mod G is an affine space. If that's the case, this is always an isomorphism. And then slightly weaker than that is when V mod G is a complete intersection. Then this is always an isomorphism. But beyond those cases, it's very difficult to say anything. So the main thing that the main result here is a description of this in a certain class of examples. And these will be, G will be certain classical groups, and the representation will be a sum of copies of the standard representation and the standard plus its dual in type A. These are some recent results. So the first one I'll state is for GLN. So G is GLN. W is the standard representation CN. And then V is a sum of P copies of the standard and Q copies of the dual. W star is just the dual of the standard representation. Okay. And so the statement is that for all P and Q, this map is an isomorphism. Okay, so how do you interpret a statement like this? So the description of the ring of invariance, GLN invariance on a representation of this kind is the content of Weil's first and second fundamental theorems of invariant theory. So when you take for this representation, so what does this say? It says that the generators for the ring of invariance, this is just the classical ring, are quadratic, and they correspond to a pairing of one of these P copies of W with one of these Q copies of W star. So there's an invariant pairing between them. First fundamental theorem of invariant theory says that the generators have this description, they're quadratics. Second fundamental theorem of invariant theory says that the relations among these generators are determinantal, they're n plus 1 by n plus 1 determinants. Okay, so the fact that this map is an isomorphism says that the G infinity invariants on this big polynomial algebra are generated as a differential algebra by the classical ones and then all their derivatives. And that the relations among these various generators and derivatives all come from the determinants of the classical ones and the derivatives of the determinants. So this is a description of this ring of invariance, and you can think of this as the analog of Weil's first and second fundamental theorem in the setting of arc spaces. And so what it really says is that the arc space functor and this invariant functor actually commute for this class of examples. This is a rare phenomenon. For most representations, this doesn't hold. So there's something, these are particularly nice for such a statement to hold. The next statement says something similar for the symplectic group. So G is sp2n, W is the standard representation. V is now the sum of P copies. I don't have to take the dual because that's the same thing for sp2n. And again, for all P, this is an isomorphism. And so again, in both of these cases, when P and Q are small, if they're both less than n, then the ring of invariance is an affine space where it's a polynomial ring. And when the ring of invariance is a polynomial ring, we already know that this holds. But when P and Q are large, then these categorical quotients, V mod by G, they're not affine spaces, and they're not complete intersections. So there's no general result that says this. This requires some difficult combinatorics to prove this. Essentially, the argument is constructing a standard monomial basis for these rings of invariance. Okay, and then there's a similar result for SLN, but it's more difficult than for the others, and it's not quite as nice. So again, for SLN, I take the standard representation W, and then I take V to be the sum of a bunch of copies of the standard and a bunch of copies of the dual of the standard. And then the statement is that if P and Q are somewhat small, meaning less than or equal to n plus 2, then this map is an isomorphism. So in general, if one of these guys is at least n plus 3, then it turns out that this map that I wrote down is always surjective, but it's not injective anymore. So saying that the map was surjective, again, says that these generators, this algebra of invariance is generated by the image of this map, which is the classical generators. What are the classical generators for SLN? Well, they're the same as the generators for GLN, a bunch of quadratics that correspond to pairings of one of these copies with one of these, but there's also some determinants. Whenever P is greater than or equal to n, I can take the determinant of a choice of n copies of the standard or a choice of n copies of the dual. And all these determinants are also generators. So the third statement here, well, the second statement says that this map has a kernel. And what is the kernel? Well, it turns out that in this case, V mod mod G infinity, the arc space is non-reduced. The ring of functions has a nil radical, and this nil radical is exactly the kernel. And moreover, it can be explicitly described as a differential ideal. The description is complicated, so I won't write it down here, but it is finitely generated as a differential ideal. Okay, so it would be nice to prove similar statements for the orthogonal group, but unfortunately the methods we have don't seem to work for the orthogonal group. I would be surprised if similar statements did not hold, but we can't prove them at the moment. And also for OSP 1-2n, I would expect that some similar statements hold. We also can't prove that. Okay, so there are several different ways that these results can be applied to vertex algebras, but I'm going to just focus on a few in the remaining time. So I want to come back eventually to classical freeness of these affine VOAs of orthosymplectic type. But the way that those will be, the connection between classical freeness and these results on invariant theory are that we're able to realize these affine VOAs inside free field algebras as cosets of other affine VOAs. So more generally, these results on invariant theory allow us to say something about the structure of cosets of affine VOAs inside free field algebras. Well, not in general, but in certain nice examples that we need here. Okay, so let me take the rank n beta gamma system. So I'll call this S of n. So this is a vertex algebra that has even generators, beta I and gamma I. I runs from 1 to n. And they satisfy this OPE. So they're even, they have only a first order pole. Beta I with gamma j is delta ij. All other OPEs are trivial. Okay, sometimes these are called symplectic bosons. There's an action of the symplectic group on this. And this is the vertex algebra analog of the Weyl algebra. You take Jus algebra of this. I think this was also already mentioned in Krzyzka's talk that you get the Weyl algebra. Okay, so now let me take nm copies of the beta gamma system with some positive integers n and n. And I want to think of this as being attached to the space of n by n matrices. So there's an action of SLN, commuting actions of SLN and SLM by left multiplication and right multiplication on n by n matrices. And there's a corresponding embedding, or there's a corresponding homomorphism from the Heisenberg algebra tensor V minus n SLN tensor V minus n SLM to this beta gamma system. Okay, these all commute with each other. And there's also an action of SP2n at level minus n over 2 tensored with affine SON at level minus 2n and the beta gamma system. And these are analogous to classical Howe dual pairs inside the rank NM Weyl algebra. So if I think of, so this just denotes the Weyl algebra of rank NM, which I can think of as polynomial differential operators in the space of n by n matrices. And so there's an action of USLN, USLN, and this is just an Euler operator, C of E. This thing maps to the Weyl algebra. And there's a similar action of USP2N tensor USOMM, this Weyl algebra. These are commuting pairs. Okay. And so you can ask, I'm going to introduce some notation. So sometimes the images, so I have this map from these affine VOAs to the beta gamma system. Sometimes the images are not simple. Sometimes they are, sometimes they're not. And sometimes they're not even the simple quotient. There's some intermediate algebra. So this V tilde of an affine algebra just means the image of an embedding in a free field algebra without reference to which quotient it is. Okay. Okay, so the first thing, there's a bunch of results like this that one can prove using invariant theory of arc spaces. So I won't state them all, I'll just state one set of results of this kind. So this is about the coset of this affine VOA of symplectic type inside this beta gamma system. Okay, there's similar results in type A, which I'll just ignore for now. But so if I take the image of this SP2N at level minus M over 2 and I take the coset, then I get exactly the image of this SOM algebra inside the beta gamma system. And this is analogous to a well-known classical statement that this is now the commutant in the theory of associative algebras. So the image of this universal enveloping algebra inside the Weil algebra, I take the commutant, it's exactly the SP2N invariance, which is USON. It's the image of USON. And actually, this result has been previously proven when n is 1, and this is just an SL2. So this is in some work of Dražen, Victor Katz, Mozender, Freire, Papi, and Persay a couple of years ago. And this actually did use some results on arc space, invariants of arc spaces that were known for SL2 for much longer. It's only very recently that those were generalized to SP2N. Okay, so you get that this coset is exactly this affine BOA, and there are many more results of this kind, and then we can describe cosets of affine BOAs. Okay, so now let me say something about the case of super free field algebras. So the BC system, so E of n will be the rank n BC system. This is isomorphic to the free fermion algebra of rank 2n over the complex numbers. And it's kind of an odd analog of the beta gamma system. It has odd generators BI and CI, and these just first order pole. And there also are some embeddings of affine BOAs in BC systems. So I'm only going to write down the SP2N, SP2R pair. There are other ones as well. But so what I do here is I take 2NR copies of the BC system. So I think of this as R copies of the standard representation for SP2R. So there's an action of VR SP2N, and then there's also a commuting action of VN SP2R on this. And also I can take a free field algebra of mixed type. I can take beta gamma system of rank NN, tensor BC system of rank 2NR. And so we already saw that there's an action of V minus M over 2 SP2N in the first factor. There's an action of VR SP2N in the second factor. So I have the diagonal embedding of V minus M over 2 plus R SP2N on this tensor product. And there's also a commuting action of VN OSP M2R. And so maybe I should say something about what convention I'm using for the bilinear form on OSP M2R. So there's an SP2R, the even subalgebra, there's an SP2R and an SOM. And I choose the bilinear form so that it agrees with the bilinear form on the SP part, not on the O part. So in other words, VK SP2R is a subalgebra of VK OSP M2R. I could have chosen the opposite convention because it's just what I choose. Okay. So anyway, so something which is well known is that the first map, this is a map of affine BOAs, but it actually descends to the simple affine BOAs, which are rational. And the image, the tensor product of these is actually, this is conformally embedded in this BC algebra. And it's a recent theorem of Ostrich, Rao, and Sun that for all positive N and R, these two symplectic affine BOAs are a pair of mutual commutants, or a dual pair. So the coset of LR SP2N, and here's the other SP, and vice versa. Okay, so so it turns out that I can prove something that's more general and gives a new proof of this as a special case. So the slightly more general statement is that if I take not just the case where M is 0, but I have this beta gamma factor, then there's, instead of just being VR SP2N, there's this V minus M over 2 plus R SP2N in this larger algebra. And this affine OSP M2R algebra, which commutes with, is actually the full coset. So the coset of the SP2N algebra in SNM tensor E2NR is the OSP M2R algebra, and this tilde just means the image, whatever the image is. Sometimes it's simple, but not always, so I just use tilde to denote the image. Okay, and so in the special case that n equals 1, n equals 0, you get exactly this statement, but quite different argument for it. Okay, so the idea of the proof is that I want to use the invariant theory of arc spaces, but I want to be able to apply it not only for polynomial rings, but also odd variables. I also want some exterior algebras. And so there are some settings where you can have similar results for exterior algebras. So setup here will be G is an algebraic group. I have two different finite dimensional G modules, U tilde and U. They may end up being the same, but at the moment they could be different ones. For each J, U tilde J is going to be U tilde star, the dual module. So I have a bunch of copies of the dual module indexed by J. And I fix a basis, x1J through xmj for U tilde J. So the J tells you which module I'm in, and these are all n-dimensional. And now I take the polynomial ring on all these uj tildes. I give it a name, I call it su tilde. And this is it's a polynomial ring on many copies, and I just define a differential which raises the J index to the J plus 1 index. So this is just a slightly different notation for the functions on U infinity, the arc space of U tilde. So these different copies will just be the 0th one, the one where I take derivatives, second derivatives, third derivatives, etc. And this differential corresponds to the differential that I already defined on ring of functions on an arc space. So SU tilde is just another name for polynomials on U tilde infinity. Okay, so now I want to have something like this for U, but this will now be an exterior algebra. So Uj will be a copy of U star for all J. And now I take the exterior algebra on the sum of all of these. I can fix a basis for Uj, and let's say U is n-dimensional and J tells me which J I'm in. And I can extend the differential that I defined on SU tilde to this larger algebra, SU tilde tensor LU, LU being this big exterior algebra, by just defining it on the Y variables by raising the J index. Okay, so S of U tilde tensor LU is sort of like an arc space, except that this part of it has odd variables. And this G infinity that we know acted on SU tilde, that also acts on LU. And I can consider the ring of G infinity invariance in this tensor product. Okay? There's also the stuff which is generated by the, what I want to call a classical piece, where J is 0. The J equals 0 term generates everything as a differential algebra. So S0 U tilde will just be the polynomials on U0. L0U will be the exterior algebra just on U0, the first one. And inside there, the action of G preserves the level, it preserves which J I'm in. So G acts on S0 U tilde tensor L0U. And I can take the invariance, and then I can take the differential algebra generated by the invariance. This sits inside the big G infinity algebra of invariance that I'm interested in. And so a similar question one can ask is, when is this big algebra of G infinity invariance generated by the G invariance as a differential algebra? This is the question I want to ask. Okay, so since G acts on the direct sum of U tilde plus a bunch of copies of U, for every K, I have such an action. I can consider this specialization of the map that I wrote down before in general. So I take U tilde plus K copies of U. I take this thing mod G. Then I can take the arc space of that. There's a function from C of this arc space, coordinate ring of this arc space, to this big invariant algebra. So notice that these U's in this right now are not odd variables. I've just taken many copies of U, but these are now even variables. This is a special case of the map that I wrote down before. Okay, so there is a very restrictive condition that I want to impose, which turns out to hold in the cases that we need, which is that this map 1 is an isomorphism for all K. Okay, most of the time that won't be the case, but as we've seen, if say U is, G is the symplectic group and U tilde are both the standard representation, then this will be an isomorphism for all K. So this is the hypothesis that I'm going to impose. It holds in that case, it holds in a few other cases, it generally doesn't hold. But suppose that it does hold. If that's the case, then I get a similar description of the ring of invariance in a ring of this kind where I have some odd variables now. So this is now S of U tilde. These are the ones that are even. These are the odd variables. So if this is an isomorphism for all K, then this ring of invariance is generated by the level 0 invariance, the classical invariance. So in particular, what that means is that if we fix a generating set for the level 0 G invariant ring, then these generators will generate the G infinity invariance, that's the algebra that I care about, as a differential algebra. Okay, now suppose that, so this is just that one is surjective. So this can still have a kernel, but at least I get the generators in this setting of odd variables when this is surjective. But now suppose even more that this one is an isomorphism, not only surjective, but it has no kernel. Then I can say more. So then not only do the generators here, here come from the classical ones, but also all the relations here come from classical relations and their derivatives in this setting where I now have odd variables. So in other words, if I take generating set for the ideal of relations among these alphas, and these alphas, some of them could be odd, some of them could be even. Some of these relations can also be odd or even. I can still conclude that the ideal of generators among these alphas, which I know generate this G infinity invariant ring, the ideal of relations comes from the classical ones and their derivatives. Okay, so this is quite a strong statement. It holds in this generality. And the key to this is that one is an isomorphism for all K. Okay, so as I said, there are not very many settings where one can apply that, but one of them is the case where G is the symplectic group and both U tilde and U are the standard representation. So this, as an immediate corollary, we get classical freeness of Ln sp2r. And the reason is that I realize Ln sp2r as the invariance in a ring of invariance. Well, it's the invariance inside some free field algebra, and I tested the associated graded algebra. It's just the invariance in some big exterior algebra. And then I can use this statement to say that all the relations come from the classical relations, and that is exactly what it means to be classically free. Okay, so as I said before, this extends the result of Van Ekeren and Arnold in the case of R equals 1. And as I said before, the notion of classical freeness makes sense for vertex superalgebras. So this was introduced by Heluani, and this statement for superalgebras is algebraically, it's the same thing. If you have a vertex superalgebra, you can still take the G commutative superalgebra. RV is now a commutative superalgebra. There's still a surjective map from the RV infinity to the graded algebra, which may now be a superalgebra. If this map is an isomorphism, we say that the vertex superalgebra is classically free. And that, using the same argument, we get the classical freeness of, well, I should say in 2 steps. So the first thing was that this coset, the coset of this SP algebra inside this free field algebra was some homomorphic image of an OSP M2R algebra. Whatever this homomorphic image is always classically free. But the statement is most interesting when I know that that homomorphic image is simple. And that's where this arithmetic condition is needed to prove that that V tilde is actually the simple quotient. This actually relies on some results of Arakawa, Kreutzig, and Kawasetsu, which are not published yet, but there is a result that allows us to show that this image is the simple quotient. And so we get classical freeness for the simple quotient, which is a more useful statement. In particular, when M is 1, we get the classical freeness of the affine superalgebra of OSP 1, 2M for all positive integer M. Okay, so I think I'm a little bit over time, but I have one more slide where I wanted to say something about non-classically free examples. So as I said before, it's very difficult when this map phi from RV infinity to the graded algebra of V fails to be injected. It's very difficult to say anything about the kernel. And there's one example that's known. And so I want to just at the end say that there's a few more examples like this where we can describe this kernel. And so these examples arise again as cosets of affine algebras inside free field algebras. So my free field algebra will be the rank n beta gamma system. And I want n to be greater than equal to 3 and m to be greater than equal to n plus 3 for this to work. And so I mentioned before that there's an action of affine SLN at level minus n, and also affine SLN at level minus m on this beta-gamma system. And these tildes refer to the images. These images conformally embedded. Actually, no, I'm sorry, I'm missing the Heisenberg algebra. So the image is not conformally embedded, but this thing tensor, the Heisenberg, embeds conformally. Here's a statement about these cosets. So this V denotes the coset of the SLN inside the rank NM beta gamma system. So it contains this affine SLN. I should say that it's an extension of this thing, tensor Heisenberg. So this is not exactly right. There's an extra Heisenberg, and then it's an extension of that. What is the extension generated by? Well, there's a bunch of fields in conformal weight n over 2. There's exactly 2 m choose n of these fields. They're all determinants, either in the betas or in the gammas, and they correspond to the invariance of SLN acting on a bunch of copies of its standard representation that you don't see in the GLN invariance. So the description of the generators comes from the invariant theory of SLN. Okay, so one can show that the generators are what you expect. They're the classical things and their derivatives. The associated scheme of this vertex algebra is exactly this quotient, this categorical quotient. I'd say m copies of Cn plus its dual. So m copies of the standard plus its dual. And then I'd take the categorical quotient of this thing mod SLN. That's actually the associated scheme of this vertex algebra. And this comes from the passing to the associated graded algebra and using the results on invariant theory of arc spaces. Now the arc space of this particular categorical quotient, I mentioned earlier that in this range, when m is greater than n plus 3, this arc space is not reduced anymore. So if m was lower, this would be reduced, but it's non-reduced. It has a nil radical. We have an explicit description of the nil radical as a differential ideal, and it has finitely many generators. So the last thing that I should say is that in general, it's very difficult to describe the singular support, meaning to describe all the relations in the graded algebra. But in this case, we can. And it turns out that this singular support is exactly the reduced scheme of this arc space. So in particular, the kernel of this map is this nil radical, and we have an explicit finite generating set. It is nil radical. So unfortunately, this class of examples, it's an infinite class of examples where we have a description, but the methods don't easily generalize. And it comes from nice features of invariant theory of arc spaces for standard representations of classical groups. And if I pass to some other representation of classical groups, I'd be very surprised if such nice results hold. But at least we get a bigger class of examples where we can describe this kernel. Okay, I think I'm way over time, so let me stop here.
Any questions? Questions from the audience, perhaps? Yeah. So if there are no hands, so Andrew, do you have control over how many generators that this nil radical has?
Yes.
So you know how many?
Yeah. We know explicit description and how many. Yeah.
So that might be useful for us. And then coming back to this question of Drazen, that I may have lost it, but so this is W3 at level -3/2.
Yeah.
That you have the generator of so that the simple quotient for that one, that's boundary admissible, right? No, so it's not -3 plus 3/2.
No, the level is -3/2. It's not the shifted level. So
yeah, but -3/2 is not the same as -3 plus 3/2.
Yeah.
So that is boundary admissible, right? So
yeah.
So that's the Hamiltonian reduction of boundary admissible SL3. So
because this is not quite a Weiss vertex algebra. Let me just check this.
I think it is principal Hamiltonian reduction of this is 0, but this singlet is just quotient of the universal.
Yeah. So this is the quotient of the universal at the boundary admissible level.
Yes.
Right. So yeah, I'm not claiming that this is the Hamiltonian reduction, but you take universal W3, W at minus 3/2, level at minus 3/2, and take the quotient by this ideal generated by this specific element that Andrew took. So checking if this is classically free or not, at least you can put it in a computer and get it at to like degree 2000. You know the character of that algebra. And
well, no, this is not classically free. This example.
oh, so you know that it's not classically free.
No, it's not. Yeah.
Ah,
So
I thought that was the question of Dragan. So you
No,
know
no,
that
no,
there are
this-
other elements in that kernel.
Yeah. So in particular, what I know is that if you take the arc space of this cuspidal curve, there are some nilpotent elements. And those nilpotent elements are in the kernel. There are two elements that are nilpotent of order 3 that are in the kernel. And I think that they generate the whole nil radical, but I also can't prove that. But I can show that up to some weight.
Nice. Okay. Yeah, so I'd like to. So you have you have a finite number of elements that you suspect that they generate the whole ideal.
Yeah, but I can't prove it.
Ah, very cool.
This actually is conjectured independently in the by some algebraic geometers. So there's some work of Seebag, Julian Seebag, and collaborators on arc spaces of curves, cuspidal curves, and not just this cuspidal curve, but instead of that, I think all the cuspidal curves, there's a similar conjecture. At least a few years ago, I think this was still old, like what the description of the nil radical is.
Right. Thanks. Any more questions? All right, so let's thank Andrew again and all the speakers of today. And tomorrow it's, well, almost free, except for those that need to go to the bank, and we'll meet on Thursday.